Check it out now, y'all.
NanoHub U, online instruction.
Hello, everybody. Welcome back to NanoHub U. This is week 2 on transfer matrices. And we're actually going to start off this time with ray optical transfer matrices, and then we're going to move on to wave optical transfer matrices. And then the common theme throughout will be that we can use like a series of 2x2 transfer matrices to succinctly allow us to compose the interactions between multiple layer structures into like kind of a simple mathematical framework, as I'll explain later. So let's just talk about kind of the very basics of how do you set up a ray optic transfer matrix problem. So here the key point is the following. If you look at this diagram, you can see that we consider like an input state, which has a certain height above the middle of the optical axis in the long direction, and then it has a certain angle with respect to that same axis. And we call these y1 and theta1. And then at the output, we have something very analogous, but a height of y2 and then an angle of theta2. Okay? And so we can actually capture a lot of what's happening in the system by looking at one set of rays that are parallel before going through optical elements, and then one set of rays that are parallel after. Okay? And then we represent both the input and output states as a height yk and angle theta k. So that's kind of the key point. And so of course we could also have other states and transfer matrices such as y3 and theta3. Now, in order to turn this into a linear algebra problem, we need linearity between the input and the output, clearly. However, there's a problem, which is that if we try to directly apply a transfer even across like free space of a distance d, then actually y2, of course, depends on y1 linearly, but has a nonlinear dependence on theta1. Specifically, y2 is y1 plus d times tangent of theta1. Okay, and that's just from basic trigonometry. But there is a solution, which is called the paraxial approximation, in which you assume that the angles are small. So in that case, actually, you can basically set both sine and tangent of theta equal to theta, more or less. And then cosine theta becomes very close to 1. So in the ray optics treatment with linear algebra, then we're just going to set cosine theta equal to 1 in general. So you can see in this picture here, we have the input and output planes like before, but now instead of having this tangent of theta1, we just have y2 is y1 plus d times theta1. Okay, and then also, because we're propagating through free space, initially theta1 is equal to theta2 in this case. So if we turn this set of two equations into a matrix problem, then we get that y2 and theta2 are given by this matrix 1d 0 1 times our input y1 theta1. And so this kind of points us to more general framework than just for the case of free space, in which we represent the transfer between the initial state and the final state to be an ABCD matrix. Okay, and so then these elements in general are left unspecified, but the key point is that they don't have any direct dependence on theta and y, but instead are dependent on the materials and the geometry of the system in between the input and output. Okay, and so that's the linear relationship that we care about. Now, in the case of, say, spherical mirrors, then we can compute like a different relationship, in which basically we would say that if light was coming onto a mirror, then we would have a certain change in the angle that would be associated with basically the tilt of the normal of that mirror as the ray intercepts the mirror. And so then this gives rise to this difference between theta1 and theta2 that's given by 2 times y, the height, divided by minus r, where r is basically the radius of curvature for this mirror. Okay, and then that can also be interpreted as oftentimes a focal length. And so then actually we can translate all these terms, the thetas and the r's, into kind of the Lensmaker's equation, in which we say 1 over the distance of the image times 1 over distance of the object would be equal to 1 over the focal length, where the focal length in this case would be equal to minus 1/2 of the radius of curvature. So in that way you can see that you can form an image using a mirror, not unlike you would form an image with a lens, if the radius of curvature would be opposite in sign to the focal length of a standard lens. And then there are obviously other things you can do in order to understand what happens, like kind of at the front boundary of a mirror. Then you can actually use Snell's law. And of course, you know that Snell's law says that n1 sine theta 1 equals n2 sine theta 2, but we're in paraxial approximation, so now we reduce that to n1 theta 1 equals n2 theta 2. And then we can write that in terms of theta 2 exclusively, so divide by n2. That gives us this expression that theta 2 is n1 over n2 times theta 1. And then we subtract this extra term, which comes from the deflection of the difference delta n over n2 times y over r. And so to kind of summarize all those key points that I was bringing up earlier, like I said before, free space has a fairly easy to derive matrix element, which is 1D01, which is shown in the first line. And then when we cross a planar boundary, then we get Snell's law applied. And so instead of the identity matrix, we get an n1 over n2 in the lower right-hand corner. Add a spherical interface, then we get not only that n1 over n2, but we also get this deflection that's associated with the local tilt. And that gives us minus delta n over n2r. And then for a lens in which we basically combine such a surface with kind of the reverse surface, we multiply those together, and then we can actually summarize those as restoring the original diagonal, but then with an extra minus 1 over f term. And then a convex lens would be represented as having positive focal length, and then a concave lens would be represented as negative focal length. And like I said before, in general, we can put all these individual elements together in order to find the overall behavior of the optical system fairly easily. And so basically what's interesting is that the multiplication is in the reverse order of the physical arrangement, which may not be obvious at first, but it kind of makes sense if you think about it, because you kind of realize that the way that matrix algebra works, it has to start off by acting on the input from the right-hand side to the left-hand side. So it kind of reads opposite of the way that you would read English. So as a result, you get this composition rule that m is equal to mn times all the other matrices down to m1. And when you multiply like elements of free space, and then you eventually go back to air with different refractive indices, then you can just represent it as basically a sum of these off-diagonal terms, and then kind of a normal diagonal 1, 1 for the identity matrix. So this kind of shows like just a little more schematically like what's happening with the input to output relationship, just showing that as we start off with our input, it goes first through optical element 1, and then 2, and then 3. And so then we kind of write this as like a nested iteration in order to get our output. So obviously it passes through O3 last, so that's why we end up writing O3 first. And then after that, it passes through O2, which comes after O3, and then O1 is obviously the first element encountered, which acts directly on the input. And so then we end up with composing these matrices in the reverse order that you might think. So to give like kind of a more concrete example of what we were talking about, here's from a tutorial that's hosted by BYU showing what happens when you have like this long chain of different optical elements, which includes like a flat high index medium and a lens and a curved interface lens, as well as like a flat mirror. And so the point is that you can kind of compose all these like different parts together. And so you can see that the input is here on the left-hand side, output is on the right, but you start off by writing down the matrix element to propagate for this last distance away from the mirror. So then that becomes 1D701. And then there's also propagation through here, but of course, like you have a mirror reversal, and then you have propagation through this lens, and then you kind of keep going backwards. And so then that's how you get all those elements that are shown on the slide. So what would happen if we had not just a series of cascade elements, but they're actually periodic in nature? So that's actually a very interesting case, because then you know that the periodic structuring would mean that if you created like a ABCD matrix for one unit or one repetition, then that should be repeated multiple times with the same exact math. And so then you basically get to exponentiate your initial ABCD matrix for a single unit m times, where m is basically the number of repetitions that occur in the system. So it kind of makes sense as kind of a special case of our general rule from before. And so here's an example from the Sully and Teich textbook, which shows that if you have a series of two lenses, f1 and f2, and then they're repeated, say m times, so we don't necessarily specify in advance how many repetitions we have, we can compose this element by basically, first of all, looking at like the elementary propagation through like basically the going backwards, so starting at f2 and then working our way backwards. And so then if we compose f2 as well as the free space right in front of it, then that will give us this matrix element. So this is just the product of 1D01 times 1, 0 minus 1 over f and 1, right? And so then that gives us this matrix. And then we can use the same rule for the second matrix, except now we have a different focal length. Multiply those together, then we get something like this. And without going through all the details in the math, actually the key point here is that we find that the magnification that's allowed in this system has to be limited. And so we kind of define a magnification factor as kind of the average of the upper left and lower right matrix elements. And that's kind of the ratio of y1 over y, or y2 over y1, and then theta 2 over theta 1. So then the average of those two factors should be less than or equal to 1. The reason is because if it was greater than 1, then that would mean that our beam kept expanding and expanding. So after enough iterations of this periodic system, it would basically become infinitely wide, obviously not physical. And so then this allows us to basically use that mathematical condition and then rearrange some of the terms. And so then this gives us this so-called stability condition for the periodic system of lenses. And so we have to fall within this range in order to be able to repeat this an arbitrary number of times without losing our beam. And then what's nice about this is it makes no specific assumptions about the initial size of the beam. All we're assuming is essentially that the beam is not getting any larger than it started off. So as long as it works initially, it should work at the end. And because, like I said before, a mirror can act in a very similar fashion as a lens, then we can also use a curved mirror to basically create like a periodic system as well, if we group two of these mirrors together. And so you see here, we basically have these two mirrors that are reflecting light back and forth between them. Obviously, the most straightforward way is to bounce directly back and forth. That's a very special case. In more general case, then we'll be basically going back and forth in a loop, kind of like a figure 8. And in that case, actually, we don't have to redo the math, which is kind of nice, because we know that the focal length of each of these reflectors would be minus R1 over 2 for the first one, and then minus R2 over 2 for the second one. And so then that allows us to directly transliterate the equation we had before for stability to the resonant mirror case. And so then that gives us this product of these two terms, 1 plus d over R1 and 1 plus d over R2. And then we can write each of the terms in succession as G1 and G2. And then the product of those two factors has to be between 0 and 1. And so this is actually a very general rule that can be used to design laser cavities, for example, in order to make sure that laser cavities will create like a stable beam upon many reflections. And so as you can see on this stability diagram, we have like a range of allowed values, which are kind of shown in the white areas. So basically up here and then down here. The grayed areas are not allowed, of course, but the borders are, because that's satisfying the equality condition. And so you can see that the regimes that are allowed, or the specific sets of mirrors that are stable, go all the way from just like kind of a pair of planar mirrors, which is the most easy to understand, and then a symmetric confocal set of mirrors in which light basically reflects back and forth like this, as you can see. And each mirror focuses light on the other mirror until it basically goes in a loop. Symmetric concentric, where it kind of focuses right in the middle. And then basically pairing like a planar mirror with a confocal mirror, which is shown here as D. And then finally, part E has both a converging and diverging mirror, but the overall convergence is positive, so the beam doesn't go away too fast. So in the next lecture, we're going to talk about not only what happens like for periodic systems in ray optics, but we'll also look at wavelength scale effects, which will be particularly important for smaller designs, like especially on the nanoscale. And we'd recommend that you take a look at the numerical methods section in Joannopoulos or chapter 10. Okay, thank you.